All right, good afternoon, everybody, and welcome to this week's MCube seminar. I'm hosting today because Hugh is out of town. Today's speaker is James Ruppert. James grew up in Long Island and did his bachelor's at SUNY Albany, where he was introduced to meteorology. He then received his master's and PhD at Colorado State University, followed by a postdoc at the Max Planck Institute for Meteorology in Germany. James is now an assistant professor at the School of Meteorology at the University of Oklahoma. Outside of work, James enjoys surfing, scuba diving, and anything in the water, which I wonder how he gets to do it in Norman, Oklahoma. Anyway, James is here this week visiting us for a meeting about cloud radiative effects, and today he will be talking to us about how the cloud greenhouse effect reconciles the stratiform complex. Take it away, James.
Thank you, Rosie. That's on. So the solution is travel, but also a well-kept secret that I didn't recognize until I moved to Oklahoma. I think I've met more scuba divers living in Oklahoma than anywhere else growing up in my life, and that includes after growing up in New York. So bizarre, but you can dive the lakes. Lake Thunderbird? I wouldn't. Yeah, I wouldn't, but if I were to describe the lake where I got my open water certification, it would probably sound far worse. So I'll save that for Q&A time. So yeah, the title here, what I'm speaking about today, how the cloud greenhouse effect, so I'll try to provide a definition for that, and what the stratiform paradox is in my mind, because this is, I'm going to go out on a limb and say that this is not some community-recognized paradox that we've all been trying to solve. So I'm going to try to set that stage and then try to put these pieces together. And what's in the background here, it has very little to do with stratiform. I just think it's a very pretty picture. Something taken from the deep tropical Atlantic last summer while we were out at sea trying to sample clouds and convective organization in the Atlantic ITCZ context. But what is intriguing about this to me in the context of what I'm talking about today is I think what there is a lack of, very high, very sort of robust, widespread stratiform and anvil clouds might be very interesting for radiative feedback and potentially a lack thereof, a lack of the importance of that in this ITCZ context, at least when those clouds aren't important. So I'll try to convince you of that by the end. So I have a lot of people to thank, and actually the list just keeps getting longer. So this week we've had other people, so some of the team who I'm acknowledging here for this specific talk weren't able to be present this week, but then also everyone who participated this week in our NCAR workshop. I also have to thank because we've been talking about some of these feedbacks, how to interpret some of this. So I've found this week to be really phenomenal for chewing through this problem. So a huge shout out to Rosie for hosting us this week and NCAR. A huge shout out to to NSF for supporting this work, for supporting NCAR, allowing us all to be here, and all of the teammates who have supported this work, both colleagues and students. So I'm going to start off with a big picture, what I think is knowledge, and then try to back that up. What we think we know about cloud radiative feedback, which I will abbreviate as CRF in a lot of cases, accelerates convective upscale development. And in the rotating context, we could say accelerates tropical cyclogenesis. And both of those things are true, at least depending on, well, across a robust sampling of model frameworks and theoretical thinking, especially the radiative feedback in the longwave, so the infrared interaction with cloud, right? And sometimes it's that infrared or longwave interaction with cloud, infrared trapping, so it gets this name additionally as the cloud greenhouse effect, a localized anomalous warming tendency. So I'm going to try to span the many scales at which we've thought about as a community this feedback. So we know on the planetary scales, it's important to the maintenance of the MJO. It's important to climate feedback and climate sensitivity. So on the time scale, interannual and longer on trends and so forth. Right? So it's important at the largest scales from the context of energy budgets, as well as mechanism denial, model simulations, and so forth. and too many citations to reference here, but I've included just a sampling. Something that I think has very strongly shaped our understanding of this feedback, especially for bringing it down in scale, is idealized theoretical frameworks, what we've come to know as RCE frameworks, radiative convective equilibrium simplified model frameworks, where they're not simple in the sense that we include everything that we think is important as far as cloud physics, radiation, their interaction, turbulent motions and response, but very simplified boundary conditions, fixed ocean temperature, and so forth. There's a long list of simplifications, to be fair. But under these very simplified environmental conditions, what you find is that radiative feedback, especially in the long wave alone, can drive convective upscale development, or TC genesis, right? So in other words, this framework really suddenly makes the case that radiative feedback is relevant to storm scale dynamics. Whereas for decades of study and advancement in our understanding of radiative balance, radiative feedback on climate scales, that's sort of a separate thing, right? And so we're starting to see a lot of overlap now as we come down in scale, or connection, let's say, links across these scales. I'm going to jump into the TC-specific context for a few of these background pieces. Specifically here, I'm leaning on some work that leveraged a realistic model framework. So by realistic, I mean it was a WRF model framework in a case study context. And where this uptick here, we're looking at short time scale of TC genesis, where in the experiment, Melhauser and Zhang modified the radiation scheme in the following ways. So a control simulation in the black is as in, let's say, nature, to the best we know. In the red, it's if you only include the night phase of the diurnal cycle, whereas in the magenta, no radiation included at all, and then a day only in the blue. And so from this time series of relative vorticity to sort of encapsulate the TC development, you see that when you only include the night phase of the diurnal cycle, you see this more dramatic, more rapid intensification or earlier timing of genesis, right? And so Fuqing and I and others among the field have had debates, disagreements about whether the attribution here is to the diurnal cycle itself per se, or if this is actually emphasizing and highlighting radiative feedback more generally. And in my opinion, at least, it's more the former. Latter. I always mix those up, right? Including or excluding the shortwave forcing has less of an impact, especially if you have it in realistic daily averaged forcing, and it's the long wave cloud interaction that really favors development and upscale development, or TC genesis. Rosie has a paper that has shaped my understanding on this. So control case here is including no radiative forcing, and in the magenta you have a population, an ensemble of simulations including radiative interactive radiation. And you again here find that in this otherwise idealized framework, but it's realistic in the context that background shear is included. And in particular, an ensemble of, let's say, realistic mean profiles that include wind shear. So let's say the width of that population, right, that's ensemble sensitivity based on stochastic noise. For example, when you include the radiative feedback, you collapse that ensemble sensitivity, and all of the, well, more of the population of TCs will develop at a shorter time scale, right? So, and another important thing that comes out when you analyze what's actually going on is that in this radiation included experiment in the magenta ensemble, you actually find that there's weaker instability from, say, metrics like CAPE. In the radiation excluded ensemble, you find more intense CAPE. You also find more intense cold pools and downdrafts. And this is something that has really stuck with me, and trying to sort of piece together how these two things could make sense. How can we reconcile those two things fitting together? So that ends up being kind of a theme of what I'm going to discuss here. And we've tried to interpret this now in an ensemble, very small ensemble of simulations with WRF. We've done this with Hurricane Maria and Typhoon Haiyan, which we had picked these cases from sort of the standpoint of trying to target representative, modest to low wind shear events, and seeing how the radiative feedback, if and how it affects TC genesis in that context. And so the small ensemble we do here is actually from a single instance control in the black, including radiative feedback, And then we remove the radiative feedback. I don't think I've mentioned this, but we do that by making clouds transparent to the radiative forcing, excluding hydrometeors from the radiative calculations at these various restart times. So at these vertical hash marks with different colors, these are these different restarts from the control where we remove cloud. And you see that especially the earlier you do this in the life cycle of TC development, the greater impact you have on TC development. And the way we interpreted this, and I've tried to cartoon this up, is that it wasn't just about this additional heat in general coming from the radiative tendency, which is, by the way, a very small magnitude heat tendency compared to, say, latent heating in a convective core. It's absolutely minuscule compared to that. But what tends to happen is when you include that radiative forcing, the convection is sort of shepherded into a smaller scale. In terms of radius, you find that the convection gets shepherded inside of the radius of maximum winds. How, I don't know, and that's one thing we're going to try to talk about, but it does happen, right? And so if you focus the convection inside a radius of maximum winds, you've made the conditions much more, let's say, favorable for TC intensification. And boom, you've accelerated the process of TC development. Shunan, who's in the audience here somewhere, did one of the first observational studies, to my knowledge, trying to understand this feedback from the context of series satellite data. If you compare, let me talk about this metric, because this will come up some more, the longwave ACRE. I'll make a list and table of acronyms to refer back to. The longwave ACRE, or conceptually, it's the column integrated radiative forcing of cloud, right? It stands for atmospheric cloud radiative effect, used very heavily in the climate community, right? So it's meant to encapsulate the entire column's effect of clouds in the long wave in watts per meter squared units, right? And you could calculate it as shown here, difference between all sky and clear sky tendency. So if you compare the scene these are all from tropical depressions, in tropical depressions that will weaken or intensify and then take their difference, you find that intensifying tropical depressions have stronger long wave cloud radiative forcing. And observations alone, this could be circumstantial, it could be red herring and so forth, but we have the model mechanism denial tests to bring out causality in that, right? So we do interpret this as consistent with our theoretical understanding that this is an important energetic forcing. And a number of modeling studies now have confirmed that in particular the cloud ice, if you remove the cloud ice long wave feedback in a model context, you really can replicate this clouds on, clouds off experiment, right? So what we think we know, long wave cloud radiation forcing accelerates convective upscale development. Again, TC genesis in the rotating context. I'm studying this problem. What I'm going to present to you today happens to be from some TC simulations, but focusing at very early stage and trying to get at fundamental sort of process level understanding that might apply to convective, let's say, deep convective contexts more broadly, in the tropics, that is, right? And over ocean. Over land would probably be a different beast for interpreting some of these things, right? So whether we're talking very early stages of tropical cyclone genesis or convective upscale development more broadly, humor me and let's see if you agree that this might apply. So what we don't know, at least trying to put some words around my knowledge gaps that I think motivate some of what I'm going to discuss. What's special about ice in particular? I'll try to talk through that, and the title of the talk might lead you on to some hints. And then what's the physical mechanism of CRF? We've talked about, for example, as one thing, that including radiative feedback somehow consolidates the convection inside the radius of maximum wind. There's a somehow in there, right, which we don't know. How is this happening? I don't know if I'm going to fully answer that today, but that's what we're trying to push towards. And in my view, which I think is right, it has to be acting in an important way through convective-scale processes, right? So the radiative forcing, at least the cloud radiative forcing, well, it's clearly directly happening through cloud. And in the tropics, clouds are put there by convective processes, and so it stands to reason to me that, well, to assume that there isn't some convective-scale, mesoscale circulation response to that radiative forcing that sort of drives all else would seem pretty puzzling to me. And there just has not been a lot of analysis on those scales to assess that. let alone how that then goes upscale to affect climate. So first, sort of trying to discuss, contextualize, what is it that's special about ice? I'm going to cartoon, you could formulate some hypotheses in your mind, and we'll see if we're in line. To me, I'm going to put first a definition behind how, well, we in the mesoscale, anyone who's thinking about cloud scale processes, some terminology that we're maybe very familiar and comfortable with, stratiform. Right? If we're talking about mesoscale organized convection, what makes up that ice, aside from, let's say, the relatively dynamically benign, very thin cirrus, is the stratiform and the anvil cloud. Those two really only being distinguished, in my mind, on the basis of if there's a lot of precipitation or not, but otherwise radiatively the same. So stratiform, I'm talking about the thick highlighted background sort of backdrop of this convective system, right? Otherwise garden variety mesoscale convective system. The large and very persistent, right? So large time scale also, region of ice cloud maintained by, to the best of my understanding, maintained by sort of a slower layered lifting feeding off of residual buoyancy from deep convection. It wouldn't be there without the deep convection, but then does it take on a life of its own or have impacts, knock-on effects to the convection, is what we're trying to sort of play at here. Emily, who's in the audience here, has done some work to try to quantify the role of the radiative feedback from this longwave ACRE metric across these different cloud populations that we have characterized here from a model framework. I'm going to try to make the case, well, what I think I'm arguing here is sort of non-controversial, but putting a few non-controversial pieces together, we come up with some, to me, some important takeaways that had not been documented to date. So from our model output, and I'm showing you output from it and results from it before I've described the framework, which is a no-no, but I'm going to do that anyway. We are using a convection-permitting model framework. I'm going to describe that shortly. And we've got, let's say, garden variety convection, early stages of TC development for Typhoon Haiyan specifically. And we've classified grid columns that have cloud into deep convective, congestus, shallow convective, stratiform, and anvil on the basis of column-specific information from the hydrometeors. And we've compared this to the classical reflectivity-based sort of texture algorithm, which was our basis. We've also assessed the vertical motion profiles within these categories as our sort of baseline. So we're quite confident with what this result is. And then now I'm showing you the longwave ACRE as a function of these different populations. And when you do the conditional average, just average the longwave forcing in these different categories, you find that the deep convective lights up, the stratiform and the anvil light up. So each of these three populations have very high, deep ice cloud, and actually a pretty comparable radiative forcing over a given grid column. But if we're talking about on a domain average, so the cumulative radiative forcing that might be supporting convective upscale development, now we need to be thinking about a domain average where the area fraction comes into play, and you see the deep convection dramatically drop out. And that comes about by virtue of the fact that the area fraction of the stratiform and the anvil cloud in addition are much, much larger than the deep convection. So that cloud area fraction, that's non-controversial. We're happy that the model produces a result that we know and trust from observations. I would also say that this plot here is also probably non-controversial. Put those together and you have that the stratiform and anvil should dominate in terms of the radiative forcing, a new result. So due to their large persistent area, right? And so as a consequence of that large footprint, both space and time, large radiative forcing. That leads me to the question, why so large and persistent, which I've scratched my head at. And for the life of me, I cannot find much that tries to directly, in a, let's say, focused way, try to answer that question. Perhaps it's obvious to some people in here. But here's one argument I lean on. To me, it came back, like everything else in atmospheric science, to Clausius-Clapeyron. The smallness of saturation mixing ratio, or saturation humidity in the upper troposphere, where it's extremely cold, makes it extremely hard to get rid of cloud once you have cloud there. If you have cloud there and you sublimate or evaporate any amount of cloud, you immediately saturate, supersaturate. It's very hard to get rid of it. Compare that to the lower troposphere, very easy by comparison to get rid of that cloud through turbulent mixing. So Seeley et al. Put this in a really nice simple term for my understanding in the context of anvil clouds, but I think this really translates directly over to the stratiform process as well. So towards understanding its dynamic impact.
Can I interrupt you?
Sure.
Because I think there is another aspect that is
please.
very important, which is that ice follows slowly.
Okay. Yeah.
So my point is that ice follows slowly, and you can put a lot of ice, and you usually do, but it falls slowly if you compare it to drops. I think that's, your point is valid, I agree, but I think the key point, which I think, anyway, let's maybe.
Yeah, no, that's an important comment. So the fall speed is a huge distinction between the warm rain and then the ice process cloud as well. I believe that they actually test that and in essence swap the fall speed between the species to see if you can recreate the distinct lifetimes, cloud lifetimes in the lower and upper troposphere, and it still came back to the cloud lifetime attributable to the difference in saturation specific humidity. I have to go back and check that, but yeah, this is an important, also a big distinction between those populations. Yeah.
So that's what is special about ice.
Yeah. In my opinion, yeah, a few of these things that give it the longevity, the large spatial scale, are what make ice special in the context of radiative feedback. Yeah. Towards understanding its dynamic impact, which we're, I promise, slowly moving towards, this is a metric I've calculated taking a cue from large-scale tropical dynamics. So there's a metric referred to as, I'm going to pull this up on the right here, the greenhouse enhancement factor from MJO literature, where in essence you can quantify on the large scale the amount of radiative forcing per unit precipitation, right? So how much is the radiative forcing replenishing, maintaining precipitation anomalies, right? And we can now do this simple ratio, which I calculate as longwave ACRE, watts per meter squared, divided by LV times precipitation, watts per meter squared, right? So a unitless metric. Now, but in deep convection, congestus, and so on up the chain here, and you can fill this in for your mind, the precipitation rate goes down dramatically as you go from left to right. So with precipitation very large in deep convective elements, and with comparable radiative forcing, let's say, you get a very small relative magnitude of this feedback term, or relative magnitude of the radiative heating to precipitation forcing, or to latent heating, if you prefer, right? And as you go up towards stratiform clouds and anvil clouds, precipitation rate going down exponentially, but their radiative forcing remains as strong or stronger than deep convection. So you have a very large impact of radiative forcing per unit precipitation per unit latent heating, right? So it has an outsized potential impact on the dynamics, I would say, right? This doesn't tell us actual impact, but at least from an energetic comparison, a large potential impact. So what's special about ice? We've listed a few things, but to me, boiling it down, the large scale footprint, both in space and time, right? So it has an outsized impact in terms of its domain averaged radiative forcing, but also an outsized potential impact on dynamic forcing by virtue of the fact that there is very weak latent heating, right? So let's say the mesoscale circulation coupled to the total heating is going to be strongly impacted by the radiative forcing versus the latent heating in these large-scale clouds, large-ish scale, yeah? So on to the next aspects here. What's the physical mechanism of CRF, and especially through convective-scale processes? But I first want to pause on a figure here. I never know where in the order this thing should come in, but I just know it's important. This is a figure that in tropical dynamics, it's one of the most fundamental things that we learn, one of the first things we learn when learning about statistical behavior of convection in the tropics. If you organize the tropics, this was done at first by Brotherton et al. 2004, as a function of column integrated water vapor, or precipitable water, and then plot precipitation along that integrated water path, you see this pickup, this very dramatic, well-established pickup. It varies slightly depending on the background temperature and so forth. You could account for that. What to me really jumps out here in the context of which clouds are we talking about is Ahmed and Schumacher in 2015 did this with dynamo observations, right? So it is a limited sampling to one field experiment, but over a variety of regimes, at least in the context of the MJO. And what you find is that the nonlinearity of this pickup is explained not by the pickup of, let's say, convective conditional rain rates, not by convective area fraction, not by stratiform conditional rain rate either, but by the stratiform area fraction. So increasing stratiform area fraction to first order is what explains this nonlinear pickup of rainfall in the tropics. To me, that's really important. And in addition to that, when you look at statistics of TC genesis and wind the clock back slightly, what you find is a statistically significant predictor of TC genesis and intensification is also, again, this expansion of stratiform area. So observations are trying to tell us something about the specific unique importance of stratiform that I think would be hard to sort of reconcile without thinking about what we learned from theoretical and idealized modeling frameworks related to the importance of radiative feedback. So finally coming to the mechanism I want to propose here. Water break for a moment. All right, back to my cartoon. I want to lay out what I think is paradoxical about the observations I just sort of summarized. The stratiform mode is defined by the production of cold air in the lower troposphere. Mid-level convergence or import of low moist static energy into the mid-troposphere, that produces downdrafts and cold pools, right? In many ways, this is helping to foster the demise of the convective system of the MCS and so forth. And you can also sort of characterize this by breaking up the vertical motion profile. I've done this just schematically here. Total profile in the solid, and then the convective versus the stratiform. The stratiform is what has this low-level downward motion, right? So in the average over stratiform areas, downward motion in the lower troposphere. Add the upward motion above that, and you are required to force mid-level convergence of low moist static energy air. The hypothesis here is that add the radiative feedback to that, and it helps make stratiform, instead of something that fosters the demise of the convective system, something that's actually favoring its longevity. And the idea, so I've tried to make this as sort of if you focus on the profiles, an increment to heating and cooling in the profiles. I'm trying to also account for the cloud top cooling. Don't want to leave out the cloud top cooling, even though I don't think it's fundamentally as important as what's going on all throughout the lower to mid troposphere. And that's an anomalous warming relative to the clear sky surroundings. So you add this background warming over this envelope of your, let's say, incipient tropical depression, and you've added this heating that can now affect the mesoscale dynamics. So in particular, the hypothesis is that the heating due to longwave CRF suppresses stratiform downdrafts by offsetting evaporative cooling driven by the latent processes, latent heating and cooling. I'm going to try to conceptualize this and boil this down into a metric known as precipitation efficiency. And there's several different ways to calculate this metric. There's a mass flux form that I'll actually be leaning on most heavily here. Downdraft mass flux within the column and updraft mass flux, which are related through this epsilon precipitation efficiency, right, which you could easily rearrange. You might also know this more familiarly, depending on your scales and what you think about, as the ratio between precipitation and condensation. So the amount of precipitation that could be measured at the ground per unit condensed water within the column. These aren't exactly equal because there's cloud storage, for example, right? But the reason I focus on the mass flux form of this is because what we're directly affecting by even slightly changing the heat tendency in the radiation is not something related to microphysics, but the vertical motion. That's my sort of my underlying hypothesis here, or a priori assumption. Just as a rule of thumb, so if E equals 1, so perfect precipitation efficiency, so no evaporation, no downdrafts, right? All condensation reaches the ground as precipitation. E equals 0, so completely inefficient, complete evaporation of rainfall. Everything that's condensed evaporates right back out. All produces cold pools instead of precipitation at the ground. Another sort of background reason for why I want to try to lean on this metric is because to our current understanding from our theoretical frameworks of convective systems and their evolution, whether they're going to decay or intensify with respect to time, and in particular the role of radiative feedback. It tries to bring in everything we think we know about the tropical convective system. Higher precipitation efficiency makes the tropical climate system more unstable. In essence, a convective system of a certain magnitude will have a greater tendency to intensify the higher the precipitation efficiency. And you can, if you do tend to nerd out in tropical dynamics, you actually see this often connected through gross moist stability, right? Lower gross moist stability for higher precipitation efficiency. And I'm not going to step through all of that, but there are some things I could talk offline about. So bringing this back to the context of the hypothesis here, the idea that longwave CRF increases precipitation efficiency, right? And again, I think we're leaning on, in some sense, non-controversial ideas. If you have stratiform with no radiative feedback, you have low-level evaporation of rainfall, producing downdrafts, mid-level convergence. If all you do is add some increment of heating that's not at the expense or cost or whatever, any interaction directly with the microphysics, you've offset that evaporative cooling and you've stifled the downdraft process, right? So by adding this anomalous heating from the longwave CRF, you have promoted greater upward motion, relatively speaking, right? You could think of less downward motion also. Higher precipitation efficiency if you have suppressed or shut down that evaporation mid-level convergence process. So that's the idea, and I'm going to try to show you some results that seem to be in support of that as of now. And so what I'm going to show you here is our 10-member ensemble WRF simulations, some results from that. I'll walk through the panels on the right in a moment. Those shouldn't have popped up yet, in fact. 10-member ensemble WRF simulation of very early stage TC development. We've run Haiyan and Maria simulations. Now we're increasing the number of cases and at higher resolution. But again, the point here is focusing on very early stage pre-genesis. We remove the cloud radiation forcing in a set of experiments, either for all clouds or just, say, the stratiform and anvil, and so forth, or all of the convective populations together. And then we do all of those tests as restarts from the control after a 36-hour spin-up period. So I'm only showing you the results actually from that restart time, comparing the control to our sensitivity simulations as test minus the control. So what I'm showing you in these time series here is for 3 of, let's say, the key populations of interest, the deep convective area fraction, relative to the control, which is the flat line by construct, right? We're taking its difference from control on a per ensemble member basis, stratiform fraction, and anvil fraction. Each of these experiments, if we remove the cloud radiation forcing, we see a decay of cloud area fraction in each of these populations compared to the control. But the key point of interest to me is that, well, if you do it in all of them, you get the biggest impact. That's the blue curve, right? So that's no cloud radiation forcing in all populations of cloud. But the green curves are second in line, right? And the green curves are respectively the solid, stratiform and anvil, both made transparent, or just the stratiform in the dashed line. And again, you see the impacts in the deep convective cloud, area fraction decreasing, as well as the stratiform. The anvil, not as much. It seems to decrease and plateau, but it's a smaller area fraction in total than the stratiform. So certainly, overall, we're seeing less convective and associated cloud in all of these experiments with time. So now to give you the result and then add a little bit of explanation behind it in a moment, removing CRF, I now calculate this precipitation efficiency metric from this mass flux form, and again show you the result as ensemble member difference of test from the control. So where the net numbers show up negative, you're seeing a reduction of precipitation efficiency because of removing the cloud radiation feedback, right? Removing cloud radiation interaction. So in other words, CRF seems to, interpreting this in the reverse, cloud radiation forcing or cloud radiation feedback is promoting precipitation efficiency, right? Including that interaction. And in particular, what we see from parsing it out into the different sensitivity tests is that the stratiform and the anvil are the most important for that, right? that they help to increase precipitation efficiency through their radiative forcing. So that's a bulk average over 3.5 days of simulation time, and averaging it over all of the columns identified as either deep, stratiform, or anvil, which is how I'm going to show you all of these results. If I average them over only stratiform and anvil, you see the same, only even more dramatic. If I calculate this from the microphysical form of precipitation efficiency, I show this to, number one, show that while the result doesn't look as significant from that metric, you do see a trend in the same direction. And I think what's going on here, again, is that what we're more directly affecting when we turn on and off the cloud radiation interaction is vertical motion. So we see a very robust impact in the vertical mass flux form of PE, whereas the impact in terms of precipitation divided by condensation rate, there could be a lot of knock-on effects in cloud storage, changes in cloud amount that are not directly accounted for in that. But again, you do see the same trend in this form of PE. Now viewing this transient impact as a function of time in the into the two inputs, the upward mass flux and the downward mass flux in our simulations. What's really surprising to me is that the upward mass flux is actually intensifying. So this is saying that averaging over our stratiform, anvil, and deep convective areas, and this would be the same if I only showed you deep convective, it's intensifying. So if you average over deep convective grid columns, it's intensifying when you remove the cloud radiation forcing. But the downdraft mass flux is also intensifying, and when you put them together in our neat little formula, precipitation efficiency is robustly crashing. Okay, it's a small unit change, but very significant with respect to the change we see across the ensemble, right? And so I put less into what the actual magnitude of the precipitation efficiency is versus the robustness of the impact. Now I'm going to show you some profiles, which I think is the last way we could try to parse this out. First, of the long wave cloud radiation forcing, calculated as a difference, again, test minus control. So basically you're seeing the negative of the cloud radiative heating you would expect to see in anvil clouds, just to keep the view consistent with how we've been looking at this. So when we remove the cloud radiation forcing, you're seeing greater, let me get my mouse, I never changed this to a laser pointer. Let's do that for my last 2 slides. When you remove the cloud radiation forcing, you're imposing a greater relative cooling in the lower to mid troposphere with a maximum at around 300 hectopascals. You're imposing a relative cloud top warming, which is bizarre, but that's actually what you're doing if you're subtracting off the cloud radiation forcing, right? So greater long wave cooling, emphasizing the lower to mid, to upper troposphere. Actual cooling in terms of virtual potential temperature. Look at the match in the profiles. It's quite compelling. And a drying, right? And so you see the impact of temperature. I'm showing you now the third profile is equivalent potential temperature. So there's a match between theta V and theta E that could be explained by temperature there, but the deviation between those two in the lower troposphere, explained by moisture, right? And then coupled to these effects, a change in the vertical motion. And what was also striking to me after I stared at these profiles enough is the match in the vertical structure across this row. Right? And so some of you in the room who think tropical large-scale dynamics might have a hint of where I'm going with that idea. It's posing the potentially provocative question for a tropical cyclone scale and context that there may be a vertical balance between this change in temperature tendency and the actual vertical motion we see. And at least in my head, all we can really tell from this sequence of profiles is that cause is greater long wave cooling in the CRF off tests. And that effect is the change in convection with reduced precipitation efficiency, which manifests not only in temperature, but also in moisture and vertical motion. So now zooming in on stratiform and anvil, and I'm showing you 3 different variables from left to right. What I've done is, first over the entire model domain, I've calculated the dry, I didn't define my terms here. Dry static energy is our S bar here, right? So the sum of potential and sensible heat, right? Dry static energy change with respect to time at a given location, so partial ds dt. in the left profiles, the horizontal vector advection, right? So v dot del s, and the vertical advection on the right. And the reason I wanted to look at these is to see if the left two panels, the left and center panels, are very small, then it's actually already telling us that there is a quasi-weak temperature gradient balance between, let's say, some heat tendency and the vertical motion change we're seeing. And at least to my eyes, throughout much of the lower to middle troposphere, the horizontal advection is basically nil. We do see transient temperature change in the dry static energy, especially around this cloud top level, where that happens to be, and as well in the boundary layer. But through much of this layer, you are actually seeing an approximate weak temperature gradient balance, in that the change in temperature tendency we would see, let's say, including or excluding the radiative forcing, is being offset by vertical advection. Right? And what I could do to check this is now calculate this term. What I'm showing you now in the dashed dotted lines on top of the actual lines, which are the actual vertical motion, is that vertical motion we would get if we just assumed a weak temperature gradient balance with the change in the radiative forcing, removing or including that cloud radiation forcing. And so you see over the regions where dSdt and v.∇s are negligible, you see a nearly perfect match, at least to my eyes, a very compelling match between those things. So to me, it was quite surprising, I can convince myself in hindsight, that over the scale of stratiform and anvil clouds, over these, let's say, meso beta to alpha scales, so the larger meso, it's actually maintaining an approximate weak temperature gradient balance, which is just underscoring the rapid time scale at which gravity waves act to homogenize temperature or buoyancy anomalies. So quasi-WTG balance, in particular over the lower to mid troposphere. And then finally, promise the last slide before I wrap this thing up. I have some square domain RCE simulations, so taking it back to the very idealized boundary condition forcing. These are some simulations that Allison Wing ran and shared with me. And I've calculated this same metric. First off, it was such a massive win when our cloud classification scheme just worked with the SAM model. This comes from the SAM model run at 3-kilometer grid spacing. So I've done the same calculation of precipitation efficiency over these same stratiform anvil and deep convective clouds in 2 experiments, or 2 simulations, one with CRF included. And it aggregates over time. So the convection goes from randomly scattered to very clustered over time. And then in another simulation in the orange, radiation homogenized. And so you see, first off, a big change in precipitation efficiency of these convective clusters from disaggregated to aggregated. But what I want to focus your attention on is even pre-aggregation, you see this systematic from time step 1 difference in the precipitation efficiency from this mass flux metric, whether you make clouds interactive with radiation. I should say they're interactive with radiation in both simulations, but the difference is you remove the cloud radiation feedback by homogenizing any spatial variability in the radiation in the orange simulation. And you see this incremental difference in the precipitation efficiency. So we think these results actually hold up in very idealized conditions, which to me underscores the idea that we're trying to get at core understanding of tropical convective behavior, not something that should be very specific to tropical cyclone contexts. So I've tried to convince you that stratiform and anvil clouds, which, not a new point, a key marker of upscale development. I think that does deserve greater emphasis in some of the communities that think about radiative feedback the most. That these clouds exert an outsized radiative influence on the dynamics by virtue of their large persistent scales and by virtue of the smallness of latent heating within those clouds. Their potential impact of the radiative tendency is massive compared to in deep convection. The longwave CRF, I've tried to also convince you that this anomalous warming drives upward motion, which moistens the column through vertical advection, which suppresses evaporatively driven downdrafts that would otherwise happen in the stratiform columns, right? So we can quantify this as a higher precipitation efficiency, which in turn connects to our theoretical frameworks for understanding the intensification of tropical convective systems. It destabilizes the RCE system, makes it more inclined to intensify. Some implications I think about from studying this problem: accurate representation of ice microphysics and radiative forcing is key. No one's ever heard that before, I'm sure. We have a massive amount of uncertainty and unconstrained challenges in the representation of ice microphysics. And I think the radiative feedback, the implications are that the radiative feedback only makes this problem more important to constrain for predictability challenges, with a lot of implications for prediction and hence for societal impacts of weather and climate. Another implication is that the CRF, so the cloud radiation forcing, let's say, and precipitation efficiency are fundamentally linked. And this is something that would not have occurred to me, but when you go to even our latest and greatest theoretical frameworks for RCE instability, this idea of RCE or convective systems that could be destabilized by radiative feedback, these are two independent metrics. The radiation comes in one term, precipitation in another term. And what I think these results are telling me is that those two things are actually intertwined. They're dependent on one another. I don't know if reconciling that would fundamentally change our understanding of tropical dynamics, but it's at least something that I think we haven't appreciated up to this point. Thank you very much.
Thank you, James, for a thought-provoking seminar. If there are questions, I'll hand you these. Please speak to these so our audience online can hear you as well. And for those online, please type your questions on Slido.
Thank you. Very interesting stuff. One of the exercises that I went through in the last few years is reviewing the work in GATE, since it was the 50th anniversary. And one of the things I discovered was there are a number of papers, not a giant number, but a number of papers that talk about the influence of radiation on the development of mesoscale convective systems. And the one thing they emphasized is the difference in the radiative heating inside and other heating inside the convection and outside the convection, pointing out that, you know, where the skies are relatively clear, things were cooling off at all levels and sinking. And, you know, according to Alan Betts, it didn't really change the temperature that much. The air just sank and it compensated, which seems to be a mechanism for keeping things concentrated. One of the, you focused entirely on the convection, but I wondered if you had looked at the outside as well. That's question number one.
Yeah. Had I thought about what's happening in the outside environment as well? It's actually something we talked about this week, not to just punt to our my workshop participants this week, but we have been discussing and in some sense debating or thinking about how do we parse out so what I've emphasized is pretty strictly the role of the cloud radiation forcing. So the cloud, what happens if you include clouds in the radiative transfer model, subtracting what you get if you exclude, or sorry, the total. Total minus the clear sky, so excluding them. And so is what's driving things the heating in the clouds? Is it the difference of the heating in the clouds from the surrounding environment? And I guess that last hypothetical is the same as to say, is it the gradient in the heating?
Yep.
And my suspicion, without having done this test, I tend to think that it doesn't matter that it's the specific tendency, but a tendency relative to the surrounding environment. So it's the difference in thermodynamic forcing from the surrounding environment. So there's other work, so Xunnan Wu has published work where they actually modify the clear sky radiative forcing in the surrounding environment, and you get basically a transverse circulation response to that. So I think we haven't fully parsed that out, and it's something we need to be thinking about.
Yeah. Anyway, there's some interesting papers on that from, I think, the 70s and the 80s. The other thing that just, you might already know this, but one of the big surprises we had in GATE, because, you know, being familiar mostly with Oklahoma storms, was the size of the mesoscale anvils and the amount of precipitation they produced. And Bob House and his students did a lot of that work.
Is it correct to say, so my understanding from reading some of those papers and then Bob House's stratiform, I'm forgetting the full title of it, but basically sort of a review on stratiform thinking, was that going into GATE, people really didn't expect to see stratiform or anvil, and that
Not
sort
like
of really
that.
flipped that on its head. Is that your understanding too? Do I have
Yes,
that right?
in fact, the pre-GATE meetings, the parameterizers were talking about a spectrum of deep cumulus clouds and almost nothing, well, absolutely nothing about stratiform precipitation and these deep anvils that we found when we got there.
Well, still fighting the good fight.
Yep.
No, I mean, I think all cumulus parameterization people also recognize the importance of stratiform and a variety of clouds these days. But I think now what we're trying to think about is, do these need to be more coupled? Change in thinking about how these things are coupled across scale than a cumulus parameterization, at least traditionally, might accommodate. Yeah. Thanks for the comments.
Any more questions?
Yeah, returning to what Wojtek actually mentioned earlier about the fall speed of ice. So one thing we found out early is if you have cirrus clouds, ice clouds, and you don't give them a fall speed, they last too long. And so the sedimentation is determining the lifetime of the ice clouds, which is important. And I think that's one of the most sensitive terms in climate models, is how fast the ice can fall out, because that determines the area of the cirrus clouds, or the anvils even. So I think that's where sedimentation comes in. It's one of the drivers of the lifetime and the size of the anvil clouds, and that would then have a big radiative impact.
Yeah.
And I think the studies with climate models shows that's one of the biggest sensitivities.
Yeah, and that brings to mind the Bretherton et al. 2005 paper that really underscored a lot with respect to the self-aggregation phenomenon. I believe it was in that study where that was a parameter they modified, and they totally changed the climate, and as far as how convection aggregates or not, and whether the domain gets a full coverage of anvil cloud or clusters into one space. So yeah, I definitely wouldn't dispute that that's a really important control parameter. I just have to go back to, I have to remind myself from the Seeley study how they brought that in there to try to mesh that argument with the idea of the impact just from the raw Clausius-Clapeyron argument. But yeah.
Okay, thanks.
Anybody else? Wojtek?
I have another comment. I haven't heard you talking much about melting level, because one of the things that ice brings to the picture is that you basically get more heating in the upper troposphere when you get ice, and then you get it back, especially in the tropics when there is virtually no ice at the surface, at the melting level. So that also, I think, probably plays some role in kind of the arguments that you're making, although I really don't see right away, how, but it has to be somewhere there. Just a comment, really, not a question.
No, I think you're justified in pointing out that I think I boiled a few things together here in talking through the process, what's happening around this level to drive that the development of that subsidence around mid-levels. Appreciate the comment.
Yeah. Although typically this part comes, of course, from evaporation, am I right? This negative heating coming in the stratiform, in GATE they call it Q1 and Q2. I mean, different, am I right? The convective heating versus stratiform heating. And of course, Q1, Q2 later, or maybe earlier, that has a different meaning. But I think in Alan Bett's paper, that's...
Something like that.
Yeah, Q1 and Q2. Anyway.
Yeah.
Gretchen has a question.
Very nice talk, James. Very compelling results, even if we can't quite explain it all. But sort of building off of even Peggy sort of got at the sum about what's happening outside of the clouds and in the clouds. It's, the gravity waves obviously are very curious. I mean, I wonder how much you've thought about the gravity wave response, even if you only have the latent heating on. That profile maps to several modes in the atmosphere. So you don't, and then it's always this thing of how do we get from isolated convection into a mesoscale convective system that actually has a stratiform region. There does seem to be a role of gravity waves, which we also can't quite figure out, but there's these multiple modes already just from deep convection and how there's more latent heating in the upper troposphere. Strongly see that signal in the tropics. And then the way the gravity waves translate in their magnitude does relate to whether or not there's anvil. Like, we also have some studies on that. I do not have answers here. I'm just wanting to bring in sort of thinking about the gravity wave signals in the troposphere as a possible other factor that's modifying how this all fits together.
Let's see. How do I try to bite off there?
Yeah, I don't even, it's just some...
No. I would say at the minimum, I think of them, well, in a way, it may come across as glossed over, but I think of them as sort of the invisible action of basically what we're seeing as far as a response in the vertical motion is the gravity waves. Is the gravity waves adjusting the isotropes in response to the change in either latent heat forcing or an added radiative forcing. And in essence, a gravity wave response to the radiative forcing has to be happening if we're seeing this circulation response manifesting on the whole scale of this convective system. It's the gravity waves that are basically trying to act to offset the temperature change through the adjustment of the vertical motion. So, but I don't know if that in any way addresses, let's say that the idea that there's sort of a cornucopia of different modes of gravity wave propagating through these regions, but I think it's important that they act fast.
And I think that no, that's right. I mean, that's exactly what they are. They're the adjustment mechanism, but they are also more than that. When you get into smaller scales, you're seeing that they also feed back onto the structure itself, right? Mm-hmm. They don't have no impact on organization. And so I just think there's another interesting piece here of looking at, is it that the heating due to radiation is modifying gravity waves in a way that's modifying the structure in a way that's measurable, right? So I think, that's just a comment.
Yeah, no, that's actually one of the things that kept coming up a few times this week, in fact, was the idea of trying to find ways to identify. So we know what's the first line of causality is changing the radiative forcing, but then what intermediaries, such as potentially gravity waves, are playing a really important role that we haven't yet wrapped our mind around. That fits right in with that as a potential sleeping giant that we need to wrap our hands around. Yeah, thanks,
it was the constant topic of how do we know it's A to C and not A to B to C. Another question here, and this might be the last one.
Yeah, I'm just curious if the ice crystal radiative calculations consider ice crystal shapes in any way.
Yeah.
Somebody was going to ask that today.
Yeah.
You forgot about Jerry Harrington.
Yes.
Jerry Harrington student here, folks.
I think it's important for long waves. For short wave, yes, but for long wave, probably just the mass. Just because the wavelength is so large.
So Wojtek argues that probably for the short wave, the shape is pretty important, and probably in the long wave, maybe the mass is more exclusively important. Yeah, I can't add to that. We haven't looked at that specifically. And then, of course, one of the things in the context of modeling, like choosing your model framework for running these experiments, is that different microphysical schemes couple with the radiation differently. What information is being passed to the radiation scheme? Not very long ago, they were not coupled, and you didn't have radiative forcing being affected by cloud. Not very long ago, as a matter of relative age and so forth. But
Step at a time, right?
yeah.
Okay, well, thank you everybody for coming and for your questions. Let's thank James once again.
Yeah, thanks for the questions and comments.
James will be here the rest of today, possibly tomorrow afternoon if you want to meet. Just let me know.